Okay, so you are all hooked up, all ready to go. So the next speaker for the afternoon is Jun Nishimura from KK, and he's going to talk about the infrared regularization of the Lorentzian IKKT matrix model and the emergence of the expanding universe. Go ahead, Jun.
Okay, thank you. First of all, as one of the organizers, I feel very sorry that I cannot be there, but still I'm very happy to be able to present our recent work. And this talk is based on the work in progress with these people, and some of them are in the audience, not there, but online. But most of the results I'm going to present are actually already published in this e-print, so you can take a look later. Okay, so my talk is about IKKT matrix model, which was proposed by these Japanese people in 1996 as a conjectured non-perturbative formulation of superstring theory. And the model is very simple. It's just a model of 10 bosonic and 16 fermionic matrices. And the action is given like this. So you have these bosonic matrices A mu, which has the Lorentz vector indices, mu, which runs from 0 to 9, and also fermionic matrices, which is actually 10-dimensional Majorana-Weil spinor, and it has index alpha, which runs from 1 to 16. And as is obvious from this action, the model has SO91 Lorentz symmetry of 10 dimensions. And this is the model. And you can also make a weak rotation like this to obtain Euclidean matrix model, which has SO10 symmetry. So, and this Euclidean matrix model has been studied some years ago. And in this single slide, I would like to discuss some crucial properties of this matrix model as a non-perturbative formulation of superstring theory. First, you can actually see the connection to perturbative formulations by considering type 2B superstring theory in 10 dimensions. And this you can do by looking at the worldsheet action of type 2B superstring theory. It has direct connection to this action here. And also you can think of the light cone string field Hamiltonian. This you can derive by considering some Wilson loop operators in this model. And that is one of the connections. Now, it is expected that this model is actually a non-perturbative formulation of the unique theory underlying the web of string dualities. So now people believe that all these formulations of superstring theories are kind of connected to each other by duality. And once you are able to formulate type 2B superstring theory non-perturbatively, that theory is expected to define the non-perturbative theory of superstring underlying all these dualities. And finally, I would like to mention that the model has 10-dimensional n equals 2 supersymmetry, which cannot be realized in quantum field theories without gravity. And this means that the low energy vective theory should inevitably include quantum gravity. And moreover, if you look at the supersymmetry algebra of this model, you immediately realize that the translation in the SUSY algebra is actually realized in this matrix model as by the shift of A mu by some constant times unit matrix. And this suggests that the space-time is actually represented as the eigenvalue distribution of A mu. So in this model, although you don't have space-time a priori, actually space-time is expected to emerge dynamically from the matrix degrees of freedom. So the plan of my talk is the following. First, I'm going to review some results of the Euclidean IKKT model, and then I will talk about how to regularize the Lorentzian IKKT model, and this is the new idea that I'm going to discuss today. And then I will explain how we investigate this model numerically and show you some results of the complex Langevin simulations. And well, as you see, we have very exciting results, and I'm very happy to share them with you in this workshop. And then I'm going to summarize and discuss some future prospects. Okay, so let me first briefly review the Euclidean IKKT model. As I said, this model can be obtained from the original Lorentzian IKKT model by weak rotation. So A0 is now replaced by minus I A10, and A10 is considered as Hermitian matrix. And the partition function of the Euclidean IKKT model can be written in this way with this Boltzmann weight. And if you integrate out these fermionic matrices, you get Pfaffian. And this action for the bosonic matrices looks like this, where F mu nu is defined in this way by the commutator of A mu and A nu. And with an I in front of it, this object is Hermitian. Therefore, this action is trace of Hermitian squared, which means that it is positive semi-definite. And as you see, the Euclidean model is well defined without any cutoff. And this was first shown by these people numerically and actually proved rigorously by these Englishmen. And another interesting point is that this Pfaffian that appears after integrating out fermionic matrices is actually complex valued, and the fluctuation of the phase becomes milder for lower dimensional configurations. And this has been, well, discussed to be a possible mechanism for SSB of SO10 symmetry of this Euclidean model. But on the other hand, the fact that Pfaffian becomes complex means that it is actually difficult to study this model by Monte Carlo simulation due to the sign problem. However, we have a nice method to overcome this problem, and this method was proposed by these people in early 80s, and there are some revived interest in this method, and now we can use it really to study this model. And this is the result of the complex Langevin method applied to the Euclidean IKKT model. And I'm not going to explain all the details, but we have to introduce some deformation parameter in the fermionic action, and eventually we have to send MF to 0, which is the supersymmetric point. But if you start from large deformation parameter, you have SSB of SO10 to SO7. By decreasing this deformation parameter, you obtain smaller and smaller group, and eventually at the smallest MF that we can achieve, we get SO3 symmetry only. So this is the result of this paper, and we concluded that SO10 symmetry of the Euclidean IKKT model is spontaneously broken down to SO3. And this has been predicted earlier by the Gaussian expansion method, and our numerical results seems to confirm this prediction. And there was a very interesting talk by Arpit Kumar last Saturday, and I also saw it on the video because I couldn't attend it. Next, I would like to discuss the Lorentzian IKKT model. And as you will see, it is not well defined as it is, so we have to regularize it somehow. The partition function of the Lorentzian IKKT model looks like this. And so we have some I in front of the action, which is important in my talk. But this seems to be natural from the connection to the worldsheet theory, because, as I said, this bosonic action can be interpreted as a kind of matrix regularization of the worldsheet action for the type 2B superstring theory. So from that point of view, this action contains the integration over the worldsheet coordinates. And when you make a weak rotation, you also have to make a weak rotation for the worldsheet coordinates. That corresponds to putting an I in front of the action. So we will take this definition of the partition function, But then, unlike the Euclidean model, the Lorentzian model is not well defined as it is, because this is just a pure phase factor, and this part is Pfaffian, which is just a polynomial in A. So if you integrate over A, this is not absolutely convergent. And another thing to notice here is that Pfaffian is no more complex. It is real valued, unlike in Euclidean model. Now, but how can we regularize this model? One naive approach would be just to make a weak rotation. So as I said, you have to make a weak rotation on the worldsheet and also in the target space. And that you can actually realize by just making this phase rotation for the integration variables A0 and AI in this way. So U here, if U is 0, that is the original Lorentzian model, but if U is 1, it becomes Euclidean model that I already discussed in the previous section. Okay, so if you make this, so to speak, the integration contour deformation, actually you find that the theory is always kind of bounded below. So if you write this bosonic action like this S of A tilde has this form, and this coefficient and this coefficient are both positive real for U in this region. So when you deform the path integration contour from U equals 0 to U equals 1, you always have the action bounded below. So in this way, you can kind of regularize this path integral by the contour deformation. And then, according to Cauchy's theorem, there is some very simple relationship between correlation function in the Lorentzian model and the correlation function in the Euclidean model. They are related to each other by just redefinition of these matrices by these factors. And we can easily confirm this relationship by doing complex Lagrange simulations. And for instance, trace A0 squared in the Lorentzian model is related to this quantity in the Euclidean model, and there is a phase in front. And this is the result for the Euclidean model. And indeed, in the Lorentzian model, we find this number. This is in the complex plane, so it has this phase factor, 3 pi over 4, which is precisely this one. And similar thing we can check for the trace AI squared as well. So all these are nice, but well, it means that the emergent space-time in the Lorentzian model is actually complex because of these phase factors. And moreover, it has Euclidean signature. So it's not a real space-time that we would like to get. So the question is, how can we regularize the Lorentzian IKKT model in such a way that we can get real space-time, at least at late times? That is the point. And our new idea is the following. And it's actually very simple. We actually introduce a Lorentz invariant mass term, which looks like this, which is manifestly Lorentz invariant. And you might think that these two terms has opposite signs, so you might wonder whether this is can be well defined, but there's no problem because you have an I in front, unlike in the Euclidean model. So even if this is not positive semi-definite action, you can still make the theory well defined. Okay, so our idea is to just add this mass term. And what does it mean? And then you can do the same integration. You can try to make this contour deformation as we did without the mass term, but then you end up with this action which has this mass term. And now the coefficient of trace A0 squared and AI squared are both negative for this region of U, whereas these coefficients are positive. So this means that you cannot actually deform the contour anymore if you add this mass term. So, but of course, you can still make this model well-defined based on Picard-Lefsetz theory, as you can make this oscillating integral well-defined by Picard-Lefsetz theory. But the point here is that because of this problem of the negative real part for the mass term, equivalence to the Euclidean model can be violated once you add this mass term.
I have a naive question in the previous slide.
Okay.
So here you mentioned that space-time is complex.
Yeah.
Is this something really problem, or like sometimes when people talk about this gravity, they complexify the space-time so that they have some very some geometry or some black hole background in the complex space-time. Is this something to do with that one, or nothing to do with that, such kind of some I don't know, generalization or whatever. So
yeah, I'm aware of such activities, but such complex matrix actually appears a kind of intermediate quantity when you try to calculate something, but it should not appear in the end result. And from that point of view, I think having a complex quantity for these operators is not good. But anyway, the problem is that the Lorentzian model is actually equivalent to the Euclidean model. So how can we say that our spacetime is Lorentzian? That is the problem. Yeah. And
okay, thank you for clarification.
Yeah, thank you.
Jun, I have a silly question. So you introduced a mass term here. So naively, this mass term, it violates supersymmetry. Are you not worried about that?
Yes, we are worried about that, but eventually we would like to send gamma to 0 after taking the large n limit. And then you get something different from what you have in the large n limit without gamma. That is the idea.
Okay. All right.
So this is kind of a regularization, as we are going to see later. Okay. Just to make the theory well-defined at finite n. And after taking the large n limit, we are free to send gamma to 0. That is the goal.
Okay, thanks.
Yeah, thank you for your question. Okay, so this is the main idea, and I'm going to tell you the results of this definition of the Lorentzian IKKT model. One of the things that is interesting is that once you add this mass term, the partition function has this schematic form with gamma mass term, right? As you usually do in field theory, you can redefine your fields like this with square root of gamma, and then you can make this gamma factored out in front of the action. And then when you consider a large gamma region, then you have classical solutions, namely the stationary configuration of the action dominate the path integral. That is basically this correspondence. Gamma squared corresponds to 1 over h bar. So at large gamma, you get h bar going to 0. That means classical. So at large gamma, you have the classical solutions dominate, but then you can write down the classical equation of motion, which looks like this. This comes from the IKKT action, and this comes from the Lorentz invariant mass term. You have this equation of motion, which you can solve numerically, and we did it in this paper. And surprisingly, there are infinitely many Hermitian A mu solutions which have this expanding behavior. And I'm going to tell you later how we can extract the time evolution from matrix configurations. But anyway, this is very, promising. And moreover, I would like to mention that if gamma is negative, you can still obtain many solutions, but none of them have this expanding behavior. And also in this argument here, gamma positive is very important, because when you make gamma negative, then these coefficients become real positives, and then you can make a contour deformation to the Euclidean model without any problem. So gamma, adding this mass term doesn't really change anything if gamma is negative. So the sign of the mass term is important in my talk. But anyway, when we find these classical solutions, the space-time dimensionality is not fixed at the classical level. So we obtain, for instance, 3 + 1 dimensional space-time, but we also get 2 + 1, 1 + 1, or 5 + 1 as well. So this is not fixed at the classical level, but I'm going to show you that this is fixed at the quantum level. Okay. Now, since I'm a bit running out of time, so let me briefly tell you how to investigate the model. We first diagonalize A0, this temporal matrix, in this way, and we order the eigenvalues in this way. So alpha n corresponds to late time, alpha 1 corresponds to early times. Okay, and if we diagonalize A0, we find typically that the spatial matrices has this band diagonal structure where off-diagonal elements become very small compared to the near diagonal elements. And then we can think of a kind of block matrix of size n like this, and then we can think of this submatrix to describe the state of the universe at time t, which is the average of the eigenvalues of A0 in this region. Okay, that is how we can extract the time evolution of space as a function of time from this matrix configuration. And I will show you explicitly how this band diagonal structure comes out in our simulation, which is actually a non-trivial dynamical property. Okay, well, when we apply the complex Langevin simulation, we have to be careful because we have to complexify all the real variables into complex variables. But the question is, how can we respect the ordering of these eigenvalues, alpha 1 to alpha n? And we, in order to respect this ordering, we make a change of variables like this, where taus are all real. So after making this change of variables, this inequality is automatically satisfied. That is the trick. And once you do that, we can apply the ordinary complex Langevin method. So our effective action looks like this after rewriting everything in terms of tau for the A0s. And then the complex Langevin equation that we have to solve has this form, where t is the fictitious time evolution for the complex Langevin method, and eta are the noise term, which is basically Gaussian noise. And these are the drift terms that are basically the derivatives of the effective action with respect to the corresponding variables, tau and ai. Okay, that's what we are doing in complex Langevin method. And there are also some tricks to make the complex Langevin method work, because this is a very tricky method which requires some techniques to make it work, really. So we have to, first, we have to be careful about the Dirac operator, because if it has near zero eigenmodes, then the complex Langevin method fails. So in order to avoid that, we have to add some fermionic mass term to the action, which I already explained in the Euclidean case. But the point here is that if MF is infinity, then basically fermionic matrices decouple. So you end up with just bosonic matrix model. But MF equals 0 corresponds to the supersymmetric model that we would like to study eventually. And another trick is to stabilize the complex Langevin simulation by introducing some partial hermitizing step after each Langevin step. So if eta is 1, this basically makes AI Hermitian at each step of Langevin simulation. But when eta is small enough, we think that this is still okay. So this is, we hope that this is justifiable when dominant configurations are close to Hermitian. Okay, so those are the techniques and the method that we use to study this model. And now I would like to show you some interesting results of this simulation. And first of all, let me show you the eigenvalue distribution of this A0, the temporal matrix, for different gamma when gamma is, let's say, 1.8, small value, it looks like this. And this line here is the result for the Euclidean model, which is gamma equals 0. Okay, gamma equals 0, which is equivalent to the Euclidean model. So when gamma is small, the results are close to the what the prediction of the Euclidean model. But when gamma is large enough, you find that eigenvalues of A0 are almost real. And in particular, at late times, there is no slope. It is parallel to the real axis, which means that indeed real time emerges at late times if gamma is larger than 2 or something. And also, when you diagonalize the A0, you find the spatial matrices has this form. So basically, P and Q are the elements of the spatial matrix. And you see a very clear diagonal structure. And this occurs only when the expansion happens, as we see later. Anyway, this band diagonal structure is very important for us to extract the time evolution from matrix configurations. Now, this is the one interesting result. The time evolution of space can be extracted from the matrix configurations, as I explained. So first, let me define this extent of space like this, using the submatrix of small n by small n. Now, in the complex Langevin method, this is complex, so we can separate them into the absolute value and the phase. And now, first, let us look at the phase, theta s, which has this result for different gamma. When gamma is large enough, you find already very small at t equals 0, but if you go to later times, you find it becomes smaller and smaller. So basically, this shows that a real space emerges at late times, at least when gamma is large enough. And moreover, if you look at the absolute value of the extent of space, it has this time dependence. When gamma is large enough, you have this expanding behavior at late times. And moreover, as you go to smaller and smaller gamma, you find that the extent of time becomes longer. And therefore, you have more expansion. So as you see from this figure, gamma, the coefficient of the mass term, indeed plays the role of the infrared regulator of the expanding universe. Now, okay, another interesting point is the SSP of SO9 rotational symmetry. Let me remind you that we are using MF equals 10, so we are quite far from supersymmetric point, but then we find that the eigenvalues of the moment of inertia tensor, these are the extent of each direction of 9 space-time as 9-dimensional space. You find that only one of the eigenvalues become large, but all the other 8 eigenvalues remain small. So this implies that only one direction expands. And in particular, it implies SSV of rotational symmetry. And you can also fit this result by exponential function very nicely. And also, when you go to smaller MF, the expansion becomes more pronounced. However, there's only one direction that expands even at this value. So we may have to go to smaller MF to see whether it becomes 2-dimensional or 3-dimensional at the end. So let me wrap up. Okay, as I explained, IKKT model is a nonperturbative formulation of superstring theory, and the Euclidean model exhibits SSB of SO10 to SO3 due to the phase of the fermion determinant, or rather Pfaffian. And in fact, the Lorentzian model becomes equivalent to the Euclidean model if we define it by the formation of the integration contour. But then space-time becomes complex and has Euclidean signature. And in order to avoid this problem, we propose to introduce a Lorentz invariant mass term which invalidates the contour deformation, and it plays the role of infrared regulator for an expanding space-time. And our complex Langevin simulations show that the emergence of a real spacetime with expanding behavior as suggested by classical solutions. However, we get a one-dimensional space, at least for MF larger than 5. So the real question is whether 3D space appear at smaller MF, because MF equals 0 is really the supersymmetric point that we have to reach. Now, this is my final slide. I'll explain the mechanism of the SSP that we found here, namely the fact that we obtain one-dimensional space in the Lorentzian IKKT model. Let me first remind you that the mechanism is obviously different from that for the Euclidean IKKT model, which, as I explained, is due to phase of the Pfaffian, because the SSB in the Lorentzian IKKT model actually occurs even without fermionic matrices, so definitely the mechanism is different. Now, classical solutions with expanding behavior appears in the presence of the mass term, as I explained, but the dimensionality of the expanding space is not fixed at the classical level. So, but then you have to consider this issue quantum mechanically, and then you have to look at the bosonic action, and you immediately notice that if you have one-dimensional space, this AIAJ commutator term disappears because only one of them is non-zero. So clearly, for quantum fluctuation of the action is suppressed, most for the one-dimensional space, and that might be the reason why we get SSP. But then the question is, how can we get three-dimensional space? Well, there is an interesting suggestion here. There is actually an important property of the Pfaffian, at least for MF equals 0, the supersymmetric point. Namely, the Pfaffian is actually 0 if there are only two non-zero A mu in this argument. This was already found in this old paper. And well, this mathematical fact is the reason why we get SO9 to SO3 SSB in the Euclidean IKKT model, as we discussed in this paper. So this property of the Pfaffian suggests that configuration with at least 3D expanding space are enhanced by this effect for sufficiently small MF. And now we are trying to see whether this is true or not by simulating the model at smaller MF. Okay, thank you very much.
Okay, questions from the audience?
Thanks for such a wonderful talk. So I was curious about this taking MF going to limit to infinite limit, so where the fermions will decouple. So do we observe this emergent behavior in that model? Like,
oh yes,
would be
okay, MF equals infinity limit is just bosonic model, and we studied a lot by complex Langevin simulation, the bosonic model, and almost all the results you can obtain even in the bosonic model, even the expanding behavior, this SSB or band diagonal structure, everything. Because you see, MF equals 10 or MF equals 5 is actually not so small. So it is at least qualitatively very close to MF equals infinity, which is the bosonic model.
So this one extended dimension remains, it
yeah.
stays?
Yeah. Yes, one-dimensional space remains for the bosonic model. Yes, that is true. But we hope that at least in the opposite limit of MF equals 0, this one-dimensional space becomes 2D and 3D eventually as we decrease MF.
Okay, thank you.
Any other questions?
Toby raised his hand.
Okay, Toby.
Hi, Jun. How are you?
Hi.
That was a great talk. Thank you.
Thank you.
I mean, just maybe following up on that question, I guess Tufte conjectured this relationship between large N Yang-Mills and string world sheets. And so I guess, I mean, could it be that the 2 dimensions you're seeing is somehow some effective string world cheat? Or, I mean, maybe that's why you see it in the bosonic case as well.
I see.
I mean, I don't know. It's just a guess, but
yeah, of course, according to IKKT argument, A mu corresponds to target space. So it's not the 2D 1 plus 1D we are seeing here is target space 2 dimensions. So from that point of view, it cannot be interpreted as worldsheet, but I'm not, well, I haven't understood this connection yet. So yeah, I cannot answer that question. Sorry.
Thanks.
Okay, so I'm going to cut the discussion, and then we're going to have a 5-minute break, and then we'll try to resume and keep things on time. So Anna, just hang in there, and let's thank Jun again.
Thank you.
Can I ask one more question to Jun?
Oh, sure, please.
Yeah, so this is regarding the SUN gauge invariance. So with that eta term which you added, so as to apply complex Langevin, so doesn't that break the gauge invariance explicitly, or there is some extended gauge group like SLNC that?
Okay, so of course, if A mu are okay, so as far as ordinary SUN gauge symmetry is concerned, that process of eta does not break the gauge invariance. But in fact, in the complex Langevin method, you complexify A mu, and then the gauge symmetry is also enhanced to SLN gauge group, complex SLNC gauge group. And this eta, of course, breaks that complexified gauge symmetry. So yeah, you're right. I mean, we don't want to do that. We want to set eta to 0, but if you do that, the complex Langevin method just fails. You get just nonsense result. So yeah, that's the kind of weak point of our method. And eventually we are thinking of using other methods like leftist symbol method, for instance, which doesn't have this problem at all. But so far, well, this is all we can do.
So in this, so gauge cooling doesn't help. Like if we take eta equal to 0 and we gauge cool.
Yeah, thank you for that question. In fact, in our calculation, we already fixed the gauge by making A0 diagonal. We only treat the eigenvalues of A0 as a dynamical variable. So we cannot do gauge cooling anymore.
Okay, thank you so much.
The Zeta thing is what Ben Yeager calls dynamical stabilization.
Yeah, indeed, yeah. This eta is something like, yeah, those people are calling dynamical stabilization. Yes, you're right.
I was actually going to ask Arpit if he had looked into that, because I met up with Ben Yeager a few years ago. He was saying how it works so much better than the gauge cooling in the case of QCD.
Right. But yeah, that is true, but I still...
It's a very different setup and system.
Yeah, they claim that they get correct results, but I'm not completely sure whether that process is justifiable. Eventually, you have to send this eta to 0, also in their case, but they haven't done that.
They have mentioned that process, dynamical stabilization, that violates the complex Langevin correctness criteria. So in a way,
yeah, that's right. Yeah.
In a way,
I'll take another look at that paper.
May I also ask? So, is this somehow this lower dimensions that you get, universe that you get? Is this related to this also what you get in simulations of gravity, this polymer phases?
Quantum gravity. Yeah. We also have a similar impression when we first saw this, but well, the system is totally different from just doing quantum gravity calculations. So I'm not sure whether there is a direct connection, but yeah, as you say, yeah, branch formula is certainly a lower dimensional manifold that you get from quantum gravity. But anyway, the hope is that at the supersymmetric point, it becomes 3 + 1 dimensional spacetime. So we are not quite happy with having this 1 + 1. Yeah.